Good morning and welcome to the Big Tech Day 2025. Also here on site and in the Zoom remote stream, also a warm welcome here. I'm Hedwig Werner and I will introduce you to one of today's first speaker, Lukas Dresel. Before we can start with the first talk, I have some general remarks for you. Most of the talks will also be recorded and will be available later on bigtechday.com. Showcases and exhibits are in the main hall, if you want to have a look. And there are also different catering stations, so please distribute among them during the breaks. Otherwise, you have to wait a long time for your coffee. So, the combination of security and AI is something I find truly fascinating, and it's becoming an even more crucial topic. Therefore, I'm very honored to introduce you to Lukas Dresel. He is originated from Nuremberg and now a PhD student, a researcher at the UC Santa Barbara ZEC Lab. He's also the co-captain of the Shellfish Capture the Flag team, competing in nearly every DEF CON final since 2017, and also the Shellfish AIxCC team in DARPA's AI Cyber Challenge, where he leveraged the LLM's reasoning and memorization capabilities to improve bug discovery techniques and fuzzing. In his talk, Artificial Intelligence, LLM-driven bug hunting and patching in the AI Cyber Challenge, he will unpack the world of autonomous cyber reasoning systems, sharing insights from his team's journey that earned them a $2 million cash award in the AIxCC semifinals and led to their participation in this year's finals. At the end of the talk, we will have some time for questions. Also, the remote participants can ask questions in the Zoom chat. And that's from my side. The stage is yours.
Thank you so much. Yeah, thank you so much for the nice introduction. Glad to be here. I'm going to be giving the talk in English, but I'm also happy to take questions in German. At the end, we're very proud of the name Artificial Intelligence. Don't worry. Yeah, so we're going to start our journey here. I'll just give you, most of it was already covered, but let's talk a little bit about what I've done. This is me in Santa Barbara. I joined there in 2016, 2017 as a grad student, and we just competed in August in the DEF CON finals and the AIxCC at the same time. So this is a great way to wrap up some of that experience over the last 2 years that we did. So the Shellfish CTF team kind of consists of 3 different universities that are all collaborating together for the AI Cyber Challenge. UC Santa Barbara, Arizona State, and Purdue. And as you can imagine, with 3 universities, we have a pretty big team that comes out of it. I think like 25 to 30 people at all times that have been working on this for the last 2 years, which, it's a pretty big effort, so it makes sense. So the version that we're going to be talking about today is inspired by this great quote from Agent Smith: "Never send a human to do a machine's job." In the AI Cyber Challenge, we have to automate everything, from bug discovery to patch generation to the entire pipeline end to end. And so we're going to talk a little bit about the AI Cyber Challenge, how we got here, and the approaches we took. So starting, I want to give a quick history of DARPA Grand Challenges that led to the development of the AI Cyber Challenge in the first place. So DARPA Grand Challenges span back all the way to 2004 with the original DARPA Grand Challenge for self-driving cars. This was a bunch of cars driving in the desert, no road signs, no rules to follow. It was just a simple task of follow the road to the end of the goal. However, if we look at what actually happened in that challenge initially, the vehicles didn't make it very far. If in a couple hours, in the first couple hours, all of the vehicles had been disqualified or failed, and no team got further than 5% of the 12-kilometer track. So that's not great, right? But this is kind of the point of these grand challenges. You start with something that seems unreasonable to achieve, and then you kind of see what it gets you when you put some money into that. Within 1 year after that, we got to the next year in 2005, and now, within the span of 1 year, all of a sudden, of the 23 teams, 5 of them actually finished all the way to the end. And that kind of rapid discovery in science kind of kept going, so much so that in 2007, the Urban Grand Challenge, now the challenge had gotten so much easier for the teams to solve that we had to make it harder. There was rules to follow. You had to consider pedestrians. You had to follow the street laws. You had to deal with other cars. You had to drive in an urban environment. And I was told yesterday that actually, at the time, there was a big Techday talk about this from Mike Montemurlo, where he already described some of this. And in this much harder setting, because of all of the effort that had gone into building these systems, now 6 autonomous vehicles finished. 10 years later, now we're in a stage of robotics where there's robots of multiple different types that have been tasked in disaster recovery and underground mapping that are working together as a swarm of a bunch of these different bots, where there's drones, there's driving bots, walking bots. They're all working together to solve a task of mapping out a giant underground cave fully autonomously. And then we're continuing on. We're doing this for the military, too. They're trying to do automatic war fighting, in this case, like fighter planes, fully driven by AI. And the AI cooked the humans 5-0, and it wasn't even close. So that's nice. But for us in cybersecurity, which is really where it starts, is with the Cyber Grand Challenge in 2014. The Cyber Grand Challenge was the first DARPA Grand Challenge for computer security. And really what it looked like is something like this, where there was mostly machines that were playing autonomously capture the flag competitions. You can see a bunch of machines with a bunch of different challenge sets that are attacking and defending each other from each other. They're throwing attacks. They're trying to patch the software. And they're trying to see how far they really get, of how many of them can they patch. And at the time, the success rate was also, it was good for what these systems were built to do fully autonomously. But the winning team in the competition, which was Mayhem, competed in the DEF CON finals against the humans in that year. And the program manager said, I don't expect any Mayhem to do well. Any finish save for last place would be shocking. And true to his prediction, the machine got last. But there was a spark there, because it was actually a lot closer than that might make it seem. The machine was not last for all but the last couple hours of the competition. And the machines had automatically solved some CTF challenges in minutes that took the teams an hour plus to solve. And so that's kind of where the inspiration came from for the AI Cyber Challenge, because we've all seen what these LLMs can do. And so in 2023, in August, Perry Adams, the program manager at the time, announced the new AI Cyber Challenge with the explicit goal of automatically defending open source software and seeing how well we can make this AI stuff work that is so prone to lying to us all the time. So in the AI Cyber Challenge, the goal really is we have to build a fully autonomous system that leverages these LLMs, fixes common CWEs, especially the most critical ones that we see from command injection, SQL injections, whatever it may be, memory corruption, and not only finds the bugs, but also patches the vulnerabilities in those programs. And critically, everything is based on source code. So the rough competition structure started like this. In August 23, the initial proposals were handed in. Shellfish was awarded as one of the 7 funded teams for $1 million each. In semifinals in August last year, we had the qualifiers, where out of 42 teams, the top 7 teams placed. And and got another $2 million, and then advanced to the finals this year, where the winners took another $4 million, second place $3 million, and third place $1.5 million home. The main goal here was to reduce this average patch gap of how can AI help find these bugs fast, fix them, and then roll out these fixes much faster to users than humans normally could. And so the setting of the competition kind of operates in these three things. You get targets, which is well-known open source software, plus a harnessing environment. And your task is to first discover crashes in them. The competition was structured around crashes to ensure that the LLMs couldn't hallucinate some stuff and just make up vulnerabilities that aren't real. Every vulnerability you found had to be proven with a crashing input. And then lastly, we have to provide fixes for those crashes. Now, when we started, the first target that we were given was the Linux kernel. The Linux kernel is millions of lines of source code. In the Cyber Grand Challenge, the challenges were run a couple thousands of lines of C in a custom operating system that only had 8 system calls, no network, no file system, no nothing, extremely simplified environment. So when we looked at this, the difficulty seemed a little bit like we jumped in all the way to the Subterranean challenge of like, oh, wait, we're doing real things now. However, realistically, with all of the things that we're continuing to do and that the research community is doing as a whole, we're still probably here. So we still have yet to see that 10-year gap of what are these LLMs doing in the future and how can we get there as fast as possible. So to do that, I want to give you a quick rundown of kind of like the main techniques that we used, the main techniques that some of the other teams used, and how we built our version of the CRS artificial, and the competition in general. So obviously, the first question is like, why did we want to compete? Shellfish likes doing open source things. So we wanted to be able to create this open source CRS also because we're, working on the edge of the art is pretty fun. And we wanted to improve the state of this open source security stuff. As anyone that's done academia knows, having this outsized impact that directly makes it into projects is a little bit harder there. And takes a little bit more work, and so this is a great opportunity to do so. And the competition started 2023. ChatGPT had just been out. We were just figuring out how to use all of these LLMs. And one thing you'll see throughout the day, throughout the talk, is that we've built a lot of these agentic paradigms that everyone's doing now. At the time, none of that existed, so we had to build our own frameworks for it. And lastly, obviously, the prize pool is also not totally unappealing. OK. So for our CRS, we started out with this design principle of we have our traditional program analysis that we use, so static analysis and fuzzing that are not deterministic, but we are very well aware of the failure modes of those systems. We know when they work, we know how they work, we know why they work. And then GPT and these LLMs come along, and they're kind of like the weird third sibling that we don't really understand why they do some of the stuff they do. The output can't really be trusted. But we pretty quickly realized that we couldn't just do one of them. We had to use all of them, even though we tried to put off using them for a little bit. So the main philosophy behind our use of LLMs kind of centers around these principles. First, LLMs can solve tasks that we don't currently have solutions for that are automatic. They can reason about the semantics of the code rather than just without having to run it and without having to build custom analyses for specific pieces of code. And they operate very well on abstractions of complex logic and/or problems. But all of those have their flip side, which is everyone knows that LLMs are just as likely to give you nonsense answers a lot of the time, especially at the time of the competition where we're in the GPT 3.5 stage. That thing lies a lot. The second part, though, is that oftentimes you can change inconsequential parts. You can change a comment somewhere in the code. All of a sudden, the assessment of the LLM, whether or not that piece of code is vulnerable and/or how to exploit it, changes drastically. And an important part of the fourth part, the last part, is that abstractions that they don't know as well don't work well. And we'll go into some of the cases where this happened to us, where a lot of the times we ended up rebuilding existing tools just to fit them, retrofit them with abstractions that the LLM knows extremely well. Spoiler alert, it's Python. So the main things that comes down to is we have to pick tasks with verifiable answers so we can get around all of the nonsense. We can retry with different parameters. We can try rephrase some of the settings that we give to the LLMs, and then build feedback loops. Again, this is something that everyone does these days in the agentic loop kind of setting, but really how to construct that feedback is a pretty important part of that process. And whenever possible, we try to reuse well-studied existing abstractions for the tasks that we're trying to solve. So that ended up when the, yes. So let's talk a little bit real quick about the two modes of challenges that these systems are tasked with to understand what information we have available. The first mode of the challenge is full mode, where you get just a tar archive that contains all of the source code of that application in question with all of the logic that is in there. However, that means that the bugs can also hide anywhere in that code. And all of a sudden, if randomly somewhere there's some log4j vulnerability hiding in the logging framework that can take down your entire application, finding that piece of code that is vulnerable in that giant mess of code that you're having to deal with is a tricky problem. The second type of challenge that we're tasked with is called Delta mode, where instead of just giving you the source code of an application, the organizers will give you the source code plus some changes to be applied to that source code. And then the task for these systems, the cyber reasoning systems, is to find vulnerabilities that are introduced by those changes. In that case, you're not even allowed to report 0 days. The vulnerabilities must only exist after the changes have been applied. OK, so the general pipeline of our system is showed here at the top. We take the targets. And the first step that we're going to talk a little bit about is static analysis. So static analysis is simply analyzing the software without running it. There's a couple existing approaches. The first one we might take, especially in the full mode kind of setting, is if we're looking for Agent Smith, maybe we start by looking for people with sunglasses and suits on. The way this generally bears out is certain bug classes we can look for with syntactic patterns, for which we use semgrep, which can just find things like, hey, there's a SQL query that has a non-constant string in it. But sometimes you want these more taint-style vulnerability pattern matchings, and so we use CodeQL for a lot of that to write over-approximating queries that give us some idea of, like, here's the locations of code where there could be vulnerabilities. One nice thing about the design of our system is because we have to provide actual crashing inputs for every single crash we find, our static analysis cannot just report results. And we have to follow it up with directed dynamic analysis that tries to get us to those locations that we've identified as vulnerable. As a consequence, we can write a lot more over-approximating queries that give us a decent amount of false positives. If a certain query returns 600 false positives, but we know for a fact that every single case of a specific vulnerability is in those 600, then 600 isn't that big of a number for some of these approaches. We can actually work with that. The second part of this that is important is for the Delta mode task, where there's changes applied. Obviously, that scopes the search space of the problem massively. The vulnerabilities can either be introduced in the changes directly, or they can be enabled by those changes. And so we use static analysis to determine the blast radius of the change, if you will. Like, which functions have their behavior changed? Which functions have now become reachable that previously weren't? Which functions take values that have been changed by the changed code? that kind of thing. And we use this to get like an over-approximate area of the code that we're interested in looking in. The second thing we do, the first thing is obviously anything in those regions of code, if we have static analysis warnings in it, the value of those things should go up. The second thing, however, is we use LLMs to heavily filter down the results some more. Now, because we're doing this on query results where we know exactly what the static analysis tried to produce, we can use LLMs to filter through all of those functions and simply ask them, do you think there's a bug here? And this is the first part where I want to go into something that another team did, because it was very surprising to us that it worked and that they made it work, and it was very cool, which was the third place team, Theory. Their approach relied entirely on this. We, at some point, had the fever dream of what if we just gave every function to the LLM and asked it, do you think there's a bug here? And then you use that as a ranking metric. And we were like, no, that's insane. No one would do that. Well, it turns out they did it, and they made it work. And they actually did a lot of consecutive filtering, first with cheaper models of ranking, making the LM output like, how likely do you think there's a bug here, yes or no, highly likely, less likely. And then they use the confidence of the LM in its result as the ranking mechanism. And this was a very cool approach, very expensive in terms of LLM credits. But they made it work for them. However, we don't do that. We use all of our static vulnerability detection plus our LLM post-filtering, plus knowledge of challenge settings, like in Java, their bugs can only be in certain places. Not everywhere is command processing being done, so you can filter it out via that. And our answer to that is to use all of these over-approximating queries and then do a lot of heuristics on top of them to provide that ranking for our system. We call that code swipe. It uses the results of all of those tools plus some additional LLM prompting to get to re-rank things that are interesting in terms of like certain bug classes. And what that provides us at the end of the day is a score for each function that tells us how likely we think there's a bug, as well as some weighted information of why we think there's a bug here. Now, the main thing we do with that is we take the top 200 functions of that and give them to our directed dynamic analysis. So let's talk a little bit about dynamic vulnerability detection. Traditional fuzzing tools and traditional program analysis tools for bug discovery are very good at covering large parts of the state space of a program. libfuzzer, AFL, whatever, they pump up bugs like no one's business. And so, especially on these complex open source targets that have been fuzzed extensively already, obviously we built these into our system first. But they're very good at finding certain types of bugs. New bugs on top of that are much harder to discover. And so we need something else. So that's where all of the LLMs come in. The first approach we took is, we called it AIJON, because it's based on a research paper from RUB that is called AIJON, where basically the idea is, OK, fuzzing as a whole is a hard problem for unknown pieces of code. What if we allowed some humans to write annotations in the code that say, hey, I want this variable to be better. I want this variable to have a larger value. These two strings should be closer in value. Those kind of things. And in the paper, they show that if you do that on the coordinate system of Mario, you can make the fuzzer play Mario. So for us, we're like, hey, that sounds like a great use for LLMs. We know which functions we're trying to reach. We know what variables they're using to reach those functions. Even if we wouldn't know, the LLM can just read the code and tell us. What if we make the LLM write all of these annotations? That looks roughly something like this. This was a bug inserted in FreeRDP, where if you had a policy of some specific type, and you had too many of those policies inside the same certificate, then there was a buffer overflow somewhere down the line. The LLM inserted these annotations and said, OK, well, let me maximize the iJohn max of I. Let me try to reach as many policies as possible. Let me compare the string distance between them and try to put the correct policy in place. And this oftentimes can find that bug in minutes, where otherwise it would take hours or never find it in any reasonable amount of time. In the competition, Delta mode challenges ran for 6 hours. Full mode challenges ran for 12 hours. So we are limited in time. The second version is, well, OK, we are trying to reach specific bugs in known functions. Let's just let the LLM try to reach them directly. Let it just write the input. So Discovery Guy was our approach at this, where basically we allow the LLM to directly write a report that says, the text is not readable. I'll explain a little bit. Basically, the report includes things like, where do you think a call trace would reach that gets you from the entry point to the target? What conditions need to be met, which is the top part, to reach that vulnerable location and that vulnerability? How do you think an input would look that could get us there? What are the conditions necessary to meet it? And what it turns out is the LLMs are very good at doing this kind of task. And this is one of those cases where almost all of the competitors landed on some version of the solution of having the LLMs write Python code to generate inputs directly that they feed into the program. Because in this case, you can use any of the abstractions that the Python standard library approaches. If you had compression, the Python script could just import zlib, zlib.compress. If you had encodings or checksums, all of that could be computed and done by the LLM at the higher abstraction level that it is much better at reasoning about. Effectively, when this succeeds, we crash the target with the harness, through the harness with that input that the LLM generated. A second step here, however, is one of the tenets of our system specifically, at least, is that we want to get, obviously, as much value out of these LLMs as possible. These queries are expensive. Doing this costs you like $2-3 maybe. In the competition, we had $50,000 of LLM credits, but spread across 60 targets. So each target has maybe like $900 of LLM credits. Now, if you spend $2-3 per seed, you better want to make sure that you get good value out of that money. So if oftentimes the LLM can get us close but not get something correct, it messes something up, it puts an extra backslash somewhere that doesn't go somewhere, it misunderstands exactly how the format works. So everything the LLM produces, we give it back to our traditional fuzzing tools to mutate further and make sure that, like, if the LLM gets us close enough but not quite there, we can still get that final hurdle. And yeah, that gives us a bunch of bugs. And it turns out when the LLM does this well, the reasoning is actually pretty spot on. The LLM predicted a stack trace at the top that when we get the crash actually matches the stack trace that we see. The second version of this, where we start using these LLMs for some of the more, computationally expensive operations of combining them with fuzzing, because in the previous step, you pay those $2 for every input you generate. That means if you have $900, that's not that many inputs, right? That's like 400, 500 inputs-ish. Let's say you make it a little bit cheaper, let's call it 1,000. In the search space of the program, that's not a lot. Secondly, when your targeting of the functions that you're looking for doesn't include certain bugs, then you can never find them with the LLM guidance, because the LLM takes you to the functions that you're trying to get to, unless you get lucky with the fuzzing after that. So the next step was, OK, let's try to combine grammar fuzzing, which is a traditional technique where humans would write input specifications of this program takes this type of input, produce me a bunch of inputs from that, and then feed it to the program. We hooked that up to agents with Claude through the Nautilus fuzzer, which writes grammars like this, which, if you can't read it, it's Python again. This is the lingua franca that we found that works for everything. Everything LLM, you always use Python. Even though sometimes it puts the functions at the end when they should go at the beginning, it'll get there eventually. So in these Python grammars, you define the input structure, or more accurately, the LLM describes the input structure of the program. It can define things like, in this case, an XML grammar. In this case, we can also do one thing that the Nautilus fuzzer that we ended up using allows us to do is write rules that encode arbitrary Python operations. So this is a rule for a tar file format, which is binary packed. It has a specific, very strict header structure. The LLM is able to encode all of that in just a function in Python that takes the values it wants to place in, places them in the right places, outputs the new format, and then shoves it out to the target program when we find it. What's important here is that because the LLM is only defining the structure, it doesn't actually have to understand all of the ways in which that structure interacts together. The fuzzer can then just try millions and millions of combinations of all of these different rules and how they interact together to find these bugs automatically. And this can be complex file formats. In this case, you can have docx file formats that's a zip file structure that you iterate that has specific schemas for specific file types. It can be PDFs, PowerPoints, Excel. And most importantly, for the next step that we're going to be talking about, your grammar doesn't have to pick one. You can allow the grammar to be any of these file types. One of the targets was the Tika file parser, which is a Java project that parses 80+ file formats. Now we can just write them all into one grammar. But again, we want to get as much value out of this as possible. So what we do is we call a grammar composition, where as the LLM iterates through this, these file formats are all known file formats that are well described, and we can ahead of time write a lot of these grammars by hand via LLM usage from existing data sources like parser generators, antler grammars, or things like that, where you have a known metric of how well is my LLM doing at covering the entire grammar state space that is much more granular and directly tied to the underlying file format than fuzzing the Adobe PDF parser itself. So what we do is we generate all of these grammars ahead of time, and we can then use that information to try to pattern match each of the rules that the LLM's generated to find, like, hey, does it look like the LLM is trying to put PDFs here? If so, let's just take the entire PDF grammar we generated ahead of time, splice it into the whole grammar, and then produce inputs from that. And we do this across all of the different file system types, file types. We do this at every level of the grammar that the input wrote. So one thing that's cool is if you have an HTML file that embeds images somewhere in the middle that are base64 encoded, well, somewhere in the grammar for that rule, there's most likely a rule for an image that looks like a PNG or a JPEG. We can splice in the JPEG grammar there, and then the rest of the grammar still encodes it nicely in the way that it should be. So we'll still do the base64 encoding, now all of a sudden with way more variety of JPEGs than we would otherwise ever get out of any of these LLMs. And we then look through the code, we run these grammars, we try them out, and we see when we fuzz with them, does this produce more inputs and more functions covered than the original grammar that we used? Does this actually help explore? If so, we will take the new information and shove it out to our fuzzers and say, OK, fuzzing fleet, go pick up this grammar now and try to fuzz with that one. Now, all of these things are there to provide us with bugs. But the second stage and more important stage in terms of the scoring mechanism of the game is we also have to fix those bugs. And the first part of that is we have to understand how the bugs work and why those bugs exist. So we do root cause analysis to do this. And also here, one of the things the LLMs give us is the ability to actually somewhat understand what the code is trying to do versus what it's actually doing. And so the idea would be that oftentimes with these statistical traditional root cause analyses, you might actually be patching or identifying as the root cause the thing that's really just a symptom of the bug. And so these LLMs allow us to really kind of read the code and try to find the root cause that is deeper than just whatever caused this particular crash. And this is important because what we've seen a lot is that shallow root cause leads to shallow bug patches. Because we have a patching pipeline at the end, those patches don't fix all of the versions of that issue. In the competition, if the patch that you provide for a vulnerability, if any other competitor has a crash that bypasses that patch, your patch is invalid and gives you no points. So for this, shallow root cause is really a hard problem where if that happens, it could cost us points. So we have to make very sure that we put a lot of research effort into this part. One thing that's interesting that we found is that it's not directly obvious is a lot of the times, obviously the root cause locations are on the stack trace as the crash happens for the simple bug types, but some of the times they're not. They're in completely other pieces of the code where it was forgotten to copy a buffer and actually just returned a reference. The ownership was weird. And so we have to have some ways of recovering that information. Now, in our system, we use two different ways. We use the traditional way and we use an LLM way. The traditional way combines a bunch of existing program analysis techniques. We try to use verifiable information only as much as possible, whether that's coverage, whether that's directly through instrumentation, seeing which variables are defined where. They use a lot of heuristics that academia and industry has found to work well. One of them, for example, is some bug classes you really need dependency between variables to accurately identify where those bugs come from. Other ones you need the stack trace, other ones you need the call trace. Other ones you can identify from statistical patterns of these functions always execute when this bug happens. And we integrated most of that peer-reviewed work that we believed was worthwhile into what we call Kamushi, which is our root cause analysis that has two different modes. One that's light mode, and then we have a heavy mode that incorporates additional fuzzing on top of each crash to try to tease out like which functions are most highly correlated with that crash and that kind of thing. And what we get out of this is we get these POI clusters, the point of interest we've called them, where basically they give you groupings of functions that according to this analysis we believe should be patched together, or at least one of these functions is the patch location where that bug resides. The second version is, well, what if we just ask the LLM where the bug is? The original presentation of this, I had the meme of the monkey typing on the typewriter with GPT hooked up to the debugger, because that's exactly what we do. We basically give these LLMs the ability to read the source code in depth as much as they want, as well as use debugging on their crash locations to extract whatever additional context from runtime information they can. And the idea here is that that's how you do it as humans, right? You debug the code, you try to figure out like where did this value come from, why is it this value that shouldn't be there? We pick the points of interest and then we inspect, okay, what's the state and how does that map with what I believe the state should be? And one thing that's interesting for this part is that last point of we need a hard limit on the total capabilities. This is where a lot of the work when building these LLM systems came in, is the first approach was we just hooked up the LLM to the debugger interface directly. It could set breakpoints, it could do arbitrary things. What we found out is that it turns out it really likes dereferencing thousands of pointers in a row. And that's not really helpful when you're trying to figure out the root cause of this bug. So there's a lot of effort that went into making abstractions of these debug concepts. One would be like, set a breakpoint, and then when that breakpoint triggers, we automatically do all of the context extraction as relevant for that specific breakpoint. And giving the LLM the freedom to do these tasks did not work well for us. This is another one of those points where the abstractions really matter. If you try to give it this low-level access, it will fail. So the output of that is you get a description of what we believe the bug is. You get locations that are relevant for that bug. And then we have to patch those bugs. So this is the last stage of the pipeline, the automatic program repair. So what we're trying to do is eliminate the bugs at the root cause to mitigate a bunch of crashes at once. Now, the challenge set in the competition, this was one of the bugs that was introduced. There's some buffer overflow where the buffer is sized incorrectly at 41 characters. Turns out that's not big enough. We have to fix it. So how do we go about that? The first thing we use is we provide the LLM with any of the changes if there is a delta mode target of like, which changes are you trying to fix the bug in? This is critical for some bugs. For other bugs, it's entirely unnecessary. But for some types of bugs, it really helps for the LLM to be able to scope it to the changes necessary. The second is we give it the stack trace. And the third part is we give it a lot of tool calls that it can use to explore the source code. This is where some of our static analysis comes in again. We allow it to identify call relationships. We allow it to identify cross-references between functions to global variables, all of that kind of thing. And at the end of the day, it produces from that some amount of changes to the code that fix the bug. But we have to verify that the LLM isn't lying to us. So the first thing we have to check is, does it compile? Then we check that, do all of the test cases still pass that the software comes with? This was a critical part of the competition setting. And lastly, of course, did the crash that crashed before, does that no longer crash now? If those things are true, then you might get a patch out like this, where the buffer has been resized to 80. And that looks good at first. But remember, every patch that is bypassable could lose us points. And that patch actually was incorrect. That buffer size needs to be larger than that. And so we do additional fuzzing on top of that, additional verification, one with fuzzing our patches from the initial crashing inputs to discover if they're bypassable that way. We also send our versions of the LLM tools, like Discovery Guy, after them again and say, hey, can you try to bypass this patch for me? I think this patch is incomplete. Very important to tell it that you think it's incorrect. Try to write me an input that still exploits the program. And if that happens, then at the end of the day, you get out a verified patch. And it turns out that actually, not only do you have to adjust the buffer of the size, you have to change how much it's trying to read. It was trying to fix the wrong part of the code to fix the issue. And this actually turned out, sometimes these problems are hard. In one of the organizer inserted bugs in some of our test challenges for SQLite in this case, this pipeline was able to bypass the patch that the organizers thought correctly fixed the issue. Because it turns out that if in your encoding, actually they picked the wrong number. This should have been 5 times the size as the actual maximum, not 4 times. And the LLM agents spotted that and said, I know how to break that. And so now we have patches, we have crashes, but we need to deduplicate them to correctly identify like which bugs are we actually fixing. Not only do we have the same crash multiple times, we have different crashes from different root causes that we have to distinguish between. And one thing that's very cool about this version is, due to the nature of the competition, this is one of those cases where a lot of teams converged on the same approach again, which is actually what humans converge to when it comes to a lot of this root cause. One of the best ways is to do patch-based deduplication. You try to fix the bug, and then you see, hey, I fixed this bug. All these crashes started disappearing. Well, they were all the same crash. And these LLM-generated patch pipelines actually allow us to automate some of this. So the intuition being that if a patch eliminates multiple crashes, they are from the same bug. If 2 patches eliminate the same crash, there are probably also 2 patches for the same bug. And so we can use this information to cluster bugs and patches together into these bug clusters. And then within each cluster, patches that fix more crashes in the cluster are obviously better. However, we're scared. We don't want other people to bypass our Once we have that cluster, we can then see, hey, we have a cluster of bugs that all cluster together. We don't have a perfect patch. Now we can build meta refinement loops on top of this where we can give those back to the LLMs and say, hey, we have a patch. It's good for these cases, but we have this other crashing input that bypasses that bug. Try to produce me a better patch. And it turns out after a couple hours of this, oftentimes you end up at a correct patch. Sometimes even just randomly without the feedback loop if you just keep retrying. And it's kind of cool to see that the human-created patch-based deduplication is something that with these LLMs we can now do in real time. And then if we correctly do this, then we can actually fix the underlying root cause and eliminate all of the crashes at once. So I want to take the last minute, just to talk a little bit quickly about the results of the overall competition. During semifinals, in the first year, as you can see, this was the coverage of the bug types that were fixed by the CRSes automatically. This advanced to finals through massive improvement on all types of bugs. If you look specifically on the Java side, Java was very hard to get working because the fuzzing tools and all of that integration was a lot less developed than for C. In finals, Java has rocketed past whatever we are able to do for C now, and this was really cool to see. Secondly, from semifinals, in finals, we've gone from 37% of injected bugs found and fixed, and 25% fixed, to 77% found and 61% fixed. And the average time to patch went down to 45 minutes. And crucially, which is pretty cool, in semifinals, the competition systems found 1 C 0-day. In finals, they found 6 in C and 12 in Java projects, and automatically patched 11 of them. And so you can really see that moment from we didn't even make it past the 5% mark of the track to now we're actually kind of starting to solve the problem accurately. Awesome. With that, thank you very much.
So also, thank you very much for this great talk and a very deep insight how the system works. Do we already have some questions? Yeah, I see the first.
All right, thank you so much for the interesting talk. Now a question would be, you said in the beginning that these systems are still at the beginning of the development and all, but how expensive is it to fix what would the average cost for fixing a bug be? Is it, because it's hard to tell if you do hundreds of LLM calls, this can be really expensive, but if it's just local fuzzing tools, it just takes a bit of time, but then it's quite cheap. So do you have a rough estimate on how much it would take per bug? Is it $100, $1,000, $50, $2?
So the most expensive part is the finding. The patching is actually pretty cheap. I think our patcher spent at most ever $10 on a patch. Most of it was 50 cents to $4. The bug finding, especially when you consider things like the grammar fuzzing and the C generation, where you're just throwing as many resources as you can, in the competition, each system had $50,000 of LLM credits available to them. The team I mentioned, Theory, that used their LLM credits to do a lot of that initial breakdown of which functions are the most likely targets, they actually, every team also was given $80,000 of Azure credits to do fuzzing and all of the compute. They ended up using half of that also for Azure LLM costs to do that. So it really depends on the approach you take. In general, if you have some idea of what you're looking for, it gets pretty cheap pretty quickly. So yeah, a couple dollars if you know where you're trying to go, and then a couple dollars to fix it.
Then the next question.
Thank you for your great talk. As open source is probably the digital infrastructure of our world, Linux kernel, whatever, can you imagine a world where every open source code that is really used a lot has been checked by a system like this, and how much would it cost, and which organizations will probably do that for us?
Yeah, so this is part of the transition efforts of this program, is trying to do exactly that. So the AIxCC is partnered with the Linux Security Foundation and OpenSSF to run some of these continuously on open source stuff. One thing that didn't come through is they also partnered with Google, OpenAI, Anthropic, and Microsoft to make this work. And especially Google is known with their OSS fuzz infrastructure to do a lot of this fuzzing of at least the open source projects they care about. But which is a lot of the open source effort of like widely used libraries. And so that is part of the thing. We're also spinning out some of this into a startup, and so we're looking into, we're talking with things like open source maintainers for curl, Nginx, whatever that kind is. And from that, they're already trying to look into seeing like how can we use LLM-based bug finding and then triage to kind of, not drown in the noise of LLM-generated slop at some point, right? I think everyone's trying to both get the most value while trying to avoid some of these downsides. And yeah, I think these organizations like the OpenSSF and Google have made some commitments to doing that. And so we're trying to get it in. I know AWS is trying to do something similar, where they're trying to run the competitor systems on critical infrastructure. One part that was here is this competition was put on by DARPA and ARPA-H together. And so a lot of the settings and the target applications, especially from the Java side, were things that you would see in healthcare, like hospitals and that kind of things. And so they're interested in running it on that as well.
So there's another question. Also a reminder to the remote participants, you can also write questions in the Zoom chat.
Thank you for the presentation. One small question. You said when you started out with the project, you had to come up with basically the agentic frameworks yourself. Now that there are mature agent frameworks out there, did you embrace it, or was it too much baked into your project, the solutions you came up with?
We had already built things that worked, and so we didn't rewrite half of it because we liked our system the way it was and didn't want to have to rewrite all of it. We did adjust some of the things under the hood. So, for example, a newer version is like based on LangChain, or which upside and downsides to that. But yeah, I mean, effectively, if you think of the agentic frameworks as really just an LLM in a loop with tool calls that it can call, you don't actually need half of these fancy frameworks. A lot of it is just write some prompts. And the main engineering part is the tool calls of giving it good, true analyses. And it doesn't really matter what framework you use for that.
Good.
Thank you. Thanks for the talk. I have a question about updating to newer LLMs. Is it something you did, or were you limited by the competition anyways? And how much effort is it to just switch to a new thing because the whole thing might fall apart because it behaves differently?
Yeah, so we did a decent amount of that. By the finals, everyone's using whatever the state of the art was at the time, which for OpenAI was 03, for Claude it was Claude 4. I think upgrading to newer versions of the LLMs, we found there's some cases where we still think that like Claude 3.5 Sonnet was just better at some of the tasks than Claude 4. But overall, as long as you move within the same model family, it doesn't tend to matter that much. One thing we did see is that if you try to switch between providers or model architectures, that can have drastic consequences. For example, I can just remember from memory because I worked most on the grammar fuzzing part. For that one, if we try to use OpenAI models, that some of the models that we used were just completely unable to do that same kind of loop that Claude was doing with the prompts we'd given them. I'm sure we could have re-architected some of our prompts and rewritten some of that architecture to still work, but just like out of the box, it was just spinning, just either not doing tool calls or infinitely doing tool calls, not leading to a conclusion. That was very sensitive to the model families that we built it for, so we generally only upgraded within the same model family.
So, thank you very much. We are also done with the time, but Lukas will be here the whole day. Just approach him and ask him any other questions you have.
Yeah, awesome. Thank you so much.